Alright, ladies and gentlemen, welcome back. We're going to pick up talking about chemical bonds today. So, when we talk about compounds, those compounds are two or more elements that are held together in some sort of fixed ratio. But what's actually holding those elements together in those compounds? Well, they're chemical bonds. And when we talk about bond formation, first off, these elements, atoms, are coming together to form bonds, and it's really their valence electrons that get involved in the chemical bonding. So when we look at your electron configuration, right, so here's a sodium atom, for example. Those valence electrons are those electrons that are on the outermost orbital, or the furthest electrons from your nucleus, right? And these are the ones that aren't getting shielded by anything else, and so as a result, they're the ones that are available to form chemical bonds. And those chemical bonds are ultimately what holds atoms together in a compound. Okay, so when we talk chemical bonds, we've got two major types that we're going to deal with, and those are your ionic bonds, which is going to be the topic for today, and then we'll also talk about covalent bonds in a later video. So, first off, why do we even bother going through chemical bonding? Why do atoms join up, make these compounds? Well, it really comes down to that they want to be as stable as possible. They want to be like your noble gases, which are in that very last column of our periodic table. So they're ultimately attempting to achieve a full valence shell. That final valence orbital of their atomic structure, they want it to be full of electrons. And remember that when we talk about electron configuration, that for most elements that means that they want 8 valence electrons in that outer shell. Except remember, we've got that exception with that first row where they only have up to 2. So your noble gases themselves, they've already got that stable electron configuration. Their outer shell is already maxed out. They can't put any more electrons there, which is why they tend to not exist in anything other than their own elemental form. They don't combine readily with other elements. Everybody else, however, is working to achieve that. They're trying to be like those noble gases. But the only way for them to actually get that full valence shell is to join up with other elements, with other atoms, and help each other out in filling that way in which elements can actually achieve that stable electron configuration if they don't already inherently have it, meaning they're not a noble gas already. So one option for some of the elements on our periodic table is to go through ionic bonding. And when we talk about ionic bonding, we're talking about the transferring of electrons from one atom to another. And typically, ionic bonds happen between a metal, which is on your left side of the periodic table, and a nonmetal on the right side. Something like sodium and chloride, right? So this would be an example. And what I end up seeing is that when I take a look at my sodium atom, right, it's got 1 electron that it's then going to transfer over to chlorine. Okay? So, in order for this to work, I'm going to end up creating ions. So remember what we were talking about before. If I change the number of protons, I change the element. If I change the number of neutrons, I create isotopes. But if I change the number of electrons, I create ions. So anytime that you've got the number of protons and the number of electrons not being equal to each other, there's no longer that charge balance, they're no longer neutral atoms, and as a result I've created either a positively charged ion or a negatively charged one, depending on what happens. So if I go back to my sodium chloride here, so sodium is ultimately going to lose one of its electrons. Alright, now in order for this to work, it still has to be 11 protons because it's still sodium, right? So if I go back to this picture right here, 11 protons, right? That's what makes it sodium, so that's not going to change. But once that transfer happens, I'm now down an electron, and as a result, I've got a positive charge. And so we talk about any positively charged ion, they occur because they lose electrons, and so we call them these things called cations. Anions, on the other hand, are ions that have now gained extra electrons, like the chlorine in this example. So they're negatively charged, they've gained electrons, so anions. So same deal, if I go back, alright, in order to be chlorine, I have to stay 17 protons, so that doesn't change. But when I gain that extra electron from sodium, I'm now up an extra negative charge, and that's where that -1 comes from. Okay? Couple of ways you can remember anion versus cation. Alright, I happen to enjoy cats, so cats are positive to me, so that's one option. For those of you who aren't necessarily cat lovers, alright, that T is a plus sign. Okay, so plus, positive, that's another way to remember it. So whichever one happens to work for you. Now when we're making ionic bonds, the atoms that are involved have to include at least one positive cation plus one negative anion. That's what ultimately then comes together to make an ionic compound. That being said, I can have 2 cations and 1 anion, or 2 anions and 1 cation. It really kind of just depends. But I need at least a positive ion and a negative one, because ultimately it's those opposite charges that hold these guys together in that compound, right? So opposites attract. It's like putting a positive and a negative magnet together. That's what's going to keep those atoms together in that compound. Alright, so let's walk through some examples. So I already sort of briefly talked you through the ionic bond that happens between sodium and chloride, right? We end up creating table salt or NaCl. And what we end up seeing when we deal with this is that that sodium ion only has 1 valence electron. So this is your metal on the left-hand side of the periodic table. And typically these guys are going to be the ones who end up losing those electrons. They get rid of them. Why? Well, because if I look at sodium, it's got 1 valence electron. It ultimately needs 8 to fill that valence shell, which means I'd have to go out and gather 7 more electrons. That's energy intensive. Alright? It's way easier to get rid of 1 electron than it is to have to pick up 7 more from somewhere. So rather than going out and finding those 7, it's just going to dump off that single valence electron. It's going to get rid of it, drop down to that inner shell below, which is already full. But this doesn't matter. I can't create it, I can't destroy it, I can only put it somewhere else. So in this case, what's going to happen? Well, that electron ends up getting transferred over to a chlorine atom. Now chlorine already has 7 valence electrons. I need to get to 8, which means I only need 1 more. So why do I want to have to figure out how to dump off 7 electrons when I can just go find a single one? And that's exactly what they do. So that sodium then transfers that 1 electron to that chlorine atom. Well, now that chlorine has 8 in its valence shell. It's happy, it's stable. The sodium's happy, it's stable. And now that I've got that sodium plus that chlorine, those 2 opposite charges are going to hold these guys together into our sodium chloride atom because those opposite charges attract each other. Alright, ladies and gents, so welcome back. So we're going to pick up with covalent bonds today. So last time we were talking about ionic bonds where atoms are attempting to fill their valence shell by either accepting or giving away electrons. Covalent bonds, on the other hand, are going to occur when 1 or more electrons gets shared between atoms. So think of ionic bonds kind of like that kindergartner who hasn't really learned to share, and so one of them is taking the toy, or in this analogy, the electrons, and somebody's losing it. Covalent bonds are those really nice little kindergartners who have learned to share their toys. Alright, so covalent bonding, I've got one or more atoms that are going to share those electrons. So these electrons are going to spend time around this nucleus, this nucleus, this nucleus, regardless of where they started originally. So they travel around all of these nuclei and they're sharing those electrons equally. That's what's holding a covalent bond together, the ability for those electron clouds to essentially overlap. So there are not necessarily charges with covalent bonds. Okay. Now, we can classify covalent bonds based on how many pairs of electrons get shared. So if I'm talking a single covalent bond, something like the hydrogens here with this carbon, then they are sharing a single pair. So one of those electrons is coming from the hydrogen, the other electron's coming from carbon. And you'll often see them with just these single lines as a way to delineate a diagram of what a single covalent bond looks like. So a single pair, so a total of 2 electrons are getting shared. In a double bond, however, alright, now I've got 4 total electrons that are getting shared. So 2 originally came from this oxygen, the other 2 came from this, and you'll often see it as 2 lines, kind of like an equal sign. Or I can actually have up to a triple bond, which is what's going on here in this nitrogen model. So these 3 electrons came from this nitrogen, the other 3 are coming from here. I've got 3 total lines now, and so we're sharing a total of 6 electrons. So in covalent bonding, just like ionic, the end goal is for these atoms to have a full valence shell, which for most elements is a total of 8. And so we can share 2 electrons, and that may be enough to get everybody in the molecule happy and have a full valence shell. Sometimes it may mean we're sharing a total of 4, or maybe even all the way up to 6. Big thing here is to keep in mind that unlike the ionic bonding where I had somebody gaining electrons, as a result gaining a negative charge, plus an atom that was losing electrons and then having a negative charge, there are no charged atoms going on in covalent bonding. They're neutral atoms, and they're going to come together to form these molecules in covalent compounds. And oftentimes you'll see molecules are sort of this term we utilize across the board, or sometimes it's more specific to actual covalent molecules. We won't get too in-depth or too nitpicky about where you use that term, so long as you're talking at least about a atom joined to another atom. Alright, but a lot of times you'll see that molecule term used really strictly with the covalent compounds, and we're talking about it as the smallest unit of that covalent compound. So while I can break apart those atoms, they start to lose those properties of that compound in and of itself. So just keep in mind if you see that term specifically linked to covalent compounds, that's not uncommon, but we won't get super nitpicky about it. So let's talk about how these covalent compounds end up getting formed, and we'll use water, which is going to be a big molecule that we talk about a lot here in biology, as an example. So here I've got my oxygen molecule, and if you don't have your periodic table out, you may want to pause the video and grab it. So oxygen in and of itself, alright, has 6 electrons to itself, 6 valence electrons. Remember, the whole goal is to get to 8. Each hydrogen has 1 valence electron, and remember, he's one of those caveats. He's in that very top row, so he only needs 1 more electron to get to be like helium and be stable. So what ends up happening, well, this electron may have originally been hydrogen's, so he's going to share those electrons with oxygen. Oxygen's going to share back, and so essentially they're sharing this pair right here. So hydrogen now has the 2 that it needs, and now oxygen's up to 7. Well, the same thing's happening on this side. So this hydrogen may have originally come from, or this electron, may have originally come from this hydrogen. Oxygen's got its now 7 that it's sharing. So we share this pair. So now hydrogen's stable with the 2 it wants, and now oxygen has the total of 8 that it wants in its valence shell to be stable, happy, and have that sort of noble gas configuration. Okay, so hopefully those examples make sense. Alright, so we're going to move on just a little bit more today and talk about not only can I classify covalent bonds as single, double, or triple based on how many electrons are getting shared, but I can also talk about how those electrons are being shared. So not just the number of them, but the actual inherent sharing itself. And so that's where we're talking about polar versus nonpolar covalent bonds. Not every atom is going to share its electrons equally. Okay, so the sharing happens, but it's not happening kind of at the same rate. So we talk about a polar covalent bond as opposed to a nonpolar covalent bond. So nonpolar, if I go back to that kindergarten analogy we started with today, your nonpolar covalent bonds, all the atoms that are involved in the molecule itself have an equal sharing. They're all good at sharing their toys, right? So in this case, they're electrons. So those electrons are going to spend equal amounts of time around the nuclei of every atom involved. A polar covalent bond is somewhere in between being ionic and nonpolar. Alright, so ionic, they completely take, somebody completely loses. Nonpolar, 100% equal share. Polar covalent, I end up in the middle where some atom or atoms in that molecule have a slightly stronger attraction for those electrons. We talk about it as electronegativity. So they have a slightly stronger pull, in which case they pull those electrons to themselves around their nucleus a little bit more of the time, where some of the other atom or atoms in the molecule aren't quite as able to hang on to those electrons, and so they don't spend as much time there. So we talk ionic, it's full charge, right? So the bully versus the poor little kid who got his toy stolen. Nonpolar, completely super sweet, nice kindergarten kids, everybody's sharing, everybody gets that toy at the same amount of time. Polar covalent is somewhere in the middle, where we've got this kid who is learning to share, but isn't really perfect at it quite yet. So while they hang on to that toy for a little longer than they should, they eventually recognize they're supposed to be sharing, and so they do. Another way to think about this might be parents who are divorced versus parents who, parents who are divorced in terms of how much time those kids spend with each parent. Nonpolar, you've got a divorced family, but everybody kind of lives in the same town, and the kids can go to the same school regardless, and so they spend equal amounts of time with both parents in a given week, right? Polar covalent is more like that traditional custody arrangement where you've got the kids spending Monday through Friday with one parent because that's where they go to school and they need to be in that household at all that period of time to make sure they get to school every day. And then the other parent sees them on the weekend because that parent lives somewhere else. Alright, so electrons, or in this case the kids, are spending a bigger portion of time in one house or around one nucleus as opposed to the other. So what ends up happening is that the electrons, where they reside more often, force that molecule now to have partial charges. Okay, and I am going to be a bit of a nutcase about showing this partial charge. So when I look at it, alright, you get this squiggly little S symbol. Alright, and you have to show this Because if you don't, and all you do is do plus and minus, even though I'm going to tell you right now, you're going to see it in textbooks, you're going to see it in pictures, you're going to see it on the internet, it's wrong. Alright, please make sure that you're putting that partial charge in there, because if I just write positive or negative, it makes it seem like they're ions. And that's not what we're dealing with here. So we want to make sure we're really good in being explicit about showing that it's a partial charge, so it's still sharing those electrons. It's just that it's not sharing them equally. So if I come back over here to my water example, alright, oxygen is this big honkin' atom. It's got a stronger ability to hang on to those electrons around its nucleus more of the time than these small little hydrogens. And so what ends up happening, well, this side of the molecule ends up with that partial negative charge, okay, because it's hanging on to those electrons more. The hydrogens, on the other hand, end up with partial positives. Okay. And the reason being, they don't get to hang on to those electrons as much, so their proton, their positive charge in their nucleus, shines through a little stronger, and that's where that positive charge comes from. This is going to become really important when we start talking about water properties. So keep in mind, water is going to be sort of our classic example of a polar covalent bond. Alright. And it's going to become important because those polar molecules are then going to be able to have these additional attractions that happen between their molecules. So just like I have a positive and negative ion with opposite charges and opposite charges attract, well, I'm going to have that similar attraction going on, but now instead of it being between atoms in a compound, it's going to be between molecules in a substance. Something we talk about as intermolecular attractions as opposed to intramolecular, which would mean within the molecule itself. Now, these intermolecular attractions aren't going to be nearly as strong as a covalent or ionic bond, but they will be enough to influence some of the properties that we deal with in these polar covalent molecules. And we're going to see that when we start talking about water properties, because a lot of intermolecular attractions are responsible for the properties we see with water, because water is in fact